Good morning. My name is Dennis Bueno, and it's morning here. Today I'm going to talk to you about model checking software with arrays. This is joint work with Arlen Cox and Karim Sakala. Pretty much every C program, for example, has arrays. Arrays are difficult, first of all, because they're low level. Individual reads and writes need to be modeled, and there could be many thousands of those in a program. You have to make pessimistic assumptions when solving them. Every aliasing pair needs to be considered. And third, invariants over arrays require quantification sometimes, which is inherently difficult. Many solutions have been investigated. Separation logic, for example, in deductive verification, monadic logic, heap reachability predicates, constraint rewriting, and so on. In the SMT world, the dominant approach is the theory of arrays. The array theory was axiomatized by McCarthy. Solving the theory of arrays typically involves instantiating the array axioms. Some SMT solvers will instantiate the axioms eagerly, and some lazily in response to queries. Other SMT solvers abstract array terms and refine them on demand. Some model checkers, like Spacer, instantiate the theory axioms during reachability outside the SMT solver. Two axioms define the basic theory of arrays. They're due to McCarthy. The first says that the store operation updates an array location. The second says that store doesn't affect other locations. We also consider two more axioms. One tells us that arrays with equal elements are equal. This is also called extensionality. The other provides an operator to initialize an array to a constant. SMT solvers that use this theory keep track of their instantiations called theory lemmas. As we'll see, they probably instantiate more than necessary. What you see here is a small program with two basic blocks and an error state. The program is unsafe. The K's are distinct constants. The program assigns location 3 in B1 and locations 1 and 2 in B2. Since location 3 is K1 after B2, the error state is reachable from the initial states. Incremental inductive model checkers work backward, one step at a time, from the error state. Each step performs an SMT query. The first step is from B2 to error, during which the SMT solver will learn these two theory lemmas. The second step is from B1 to B2, during which the SMT solver will learn this theory lemma. The thing to notice here is that the first two lemmas were not used in the overall proof. So even though the SMT solver learned them lazily, they're useless to the overall proof. Now, arrays are handled in different ways in different verification flows. We want to handle them within our model checker, Euphoria, to expand the universe of programs that we can process. Euphoria is a model checker that abstracts syntactically using uninterpreted functions. So for example, add and subtract are turned into uninterpreted functions during abstraction. Euphoria targets checking programs for control properties, which is why it uses such a coarse data abstraction. And Euphoria is an incremental inductive model checker, so it uses an IC3 style algorithm and has a counterexample guided abstraction refinement loop to refine the abstraction. Euphoria is a verifier for C programs. So a C program is fed, first of all, into C-horn, which produces a bit-precise horn encoding of the program. Horn to VMT produces a transition system encoding from the horn encoding. The transition system is sent to Euphoria, which abstracts the concrete system into an uninterpreted system. Next, it performs a reachability computation on the abstracted system. This may be able to prove that the program is safe. Otherwise, an abstract counterexample is checked for feasibility. If it's feasible, then the program is unsafe. Otherwise, the abstraction produced an infeasible counterexample, so it needs to be refined. When we began this work, Euphoria only supported programs without arrays. Here's a teaser of our results. On the x-axis is Euphoria with no array abstraction, NAA. And the y-axis is width. As we will see later, the reason for this is that without array abstraction, the SMT solver learns a ton of theory lemmas, which are avoided when using array abstraction. Euphoria's array abstraction follows its data abstraction. The angle brackets denote the abstraction function, which rewrites concrete operators into uninterpreted functions. Concrete indices and values are rewritten to uninterpreted terms. Array operations are abstracted to uninterpreted functions. For instance, every store is rewritten as a store uninterpreted function with abstracted arguments. Similar thing happens with select. Both uninterpreted functions are written in all caps here. This abstraction has several advantages. Select still behaves like a function. Equal arguments give equal results. Array equality, which is commonly used in encodings, is propagated. And we also postpone learning of SMT theory lemmas until abstraction refinement. Under this abstraction, stores, constant arrays, and extensionality are over-approximated. By doing this abstraction, we avoid having the solver do any array learning, except during refinement. So let's see some examples of abstraction refinement lemmas. Euphoria learns this lemma as a constraint on uninterpreted functions during abstraction refinement. It's an instance of McCarthy's select store axiom, an instance on this particular A, I, and 0. This is another lemma, and this lemma is interesting because it is a composite lemma. It has array operations and bit vector operations in the same lemma. The way to read this is that if we store 0 at I, select from I, and extract the lower 8 bits of that result, we get 0. Euphoria learns something about store, select, and extract in a single concise lemma. We implemented our abstraction inside Euphoria and evaluated it on 948 SVComp benchmarks. Each benchmark starts its life as a C program, has all of its procedures inlined, and is converted to Horn. That Horn encoding is then converted to VMT, and we have the option of passing the Horn to a Horn solver and the VMT to Euphoria. All the solvers either return safe, unsafe, or timeout. And the timeout is 30 minutes for our experiments. So we saw these results earlier, so let's go dive into them. I've broken down the lemmas that are learned into 2 categories. They can be learned by Euphoria or learned by Z3, the underlying SMT solver. And lemmas are either generated during reachability or during refinement. Without array abstraction, Euphoria solves 227 benchmarks. 189 of those are solved without refinement. 171 of those are safe, and in total required 478 million theory lemmas across all of those 171 benchmarks. 491 benchmarks are solved with array abstraction. Of those, 400 required no refinement, and 367 of those were safe. And those required 0 theory lemmas, so 0 compared to 478. So we've solved many more benchmarks with fewer lemmas. Without array abstraction, 18 benchmarks required no refinement and were unsafe and used about 21 million theory lemmas. The corresponding set with array abstraction solved 33 with only 34K lemmas. So again, more benchmarks and fewer lemmas. Now let's look at the cases with refinement. 56 benchmarks required refinement without using array abstraction. So these would be refinements of the bit vector operations. 9 of those were safe and required about 4 million lemmas. The corresponding set, 91 required refinement and 25 were safe. Again, 25 benchmarks versus 9, more benchmarks, fewer lemmas. Out of those 56, 29 were unsafe and needed 64 million theory lemmas. And the corresponding set with array abstraction solved 66 and only required 245,000 lemmas. So in all of the categories, requiring refinement, not requiring refinement, safe and unsafe, array abstraction solved many more benchmarks and required many fewer lemmas. In order to understand these results a bit better, we also broke down the Euphoria lemmas by type. So lemmas can involve arrays or not involve arrays. Of the 91 benchmarks, so on the x-axis, we have the 91 benchmarks that required Euphoria lemmas, and the y-axis is the number of lemmas learned of each type. So from this plot, we can see that overall more bit vector lemmas are needed compared to array lemmas. The arrays aren't that important overall, despite the set being concerned with pointer reasoning. In all but 2 cases, Euphoria needed fewer than 100 lemmas, and only about 10% of the solved benchmarks needed array lemmas at all. So our abstraction seems to fit these benchmarks pretty well. So far, we've only evaluated Euphoria internally, that is, against itself. So what about other model checkers? We compared Euphoria with Spacer, version 4.8.7. We ran the Horn benchmarks and we ran Euphoria on the VMT ones. Spacer solves 386 benchmarks compared to Euphoria's 491. Euphoria solves 138 benchmarks that Spacer times out on. That's the right side band. And Spacer solves 33 benchmarks that Euphoria times out on. That's the band at the top. So let's break these results down by type. These are the same results, but just the safe benchmarks. Euphoria solves more overall, and Spacer has a significant number of timeouts on the set. We broke down the safe benchmarks also into just the safe ones that required refinement. So in this case, Euphoria's abstraction does not fit. It requires at least one abstraction refinement. Even in this case, Spacer, which is a concrete solver, solves fewer benchmarks, and overall it has more timeouts than Euphoria. This is the same data, but only the unsafe benchmarks. Again, there are still a significant number that Euphoria is able to solve that Spacer does not. So let's look at the timeouts now. Specifically these top band. So these are the benchmarks that Euphoria timed out on that Spacer did not. We looked at all of these cases and essentially determined 2 causes. In over half the cases, Spacer's preprocessor is able to solve the benchmarks, meaning no reachability reasoning was required. Euphoria's preprocessor isn't as strong. In the other cases, the benchmarks are so large that Euphoria's monolithic encoding of the transition relation dominates. Spacer uses an explicitly sliced transition system encoding, which gives it an edge on these benchmarks. These are the benchmarks for which Spacer times out, but Euphoria solves them. We looked at a large random subset of these timeouts, and in each case, either a single query is taking up all the time, or Spacer explicitly returns unknown for a particular query. So in all the cases we looked at, individual queries are responsible for Spacer's timeouts. In contrast, Euphoria uses EUF, which has efficient decision procedures and makes response times to queries relatively predictable in our experiments. In conclusion, in our benchmarks, most array learning was ultimately irrelevant for these proofs, and Euphoria's abstraction avoids computing a huge number of theory lemmas, over 478 million in aggregate. In 75% of cases, no array learning was needed at all, so the abstraction fits. And with this relatively simple modification to Euphoria, we were able to solve more benchmarks than the state of the art.